Hello, I'm Ian, and today we're going to be talking about pulling data from drawings using AI. So first, just an overview on why we might want to do something like this and what we're trying to do. We're trying to reason about large systems, think like factories, oil rigs, things like that. And we want to do things like vulnerability prioritization, deciding if we have a certain amount of effort to put towards patching, which things we want to deal with first. Putting alerts in context. If you're sitting in like an OT SOC and you get an alert, you want to know sort of how much time you have to deal with it. Is this something that you need to do right this minute, or something that'll maybe can take a few days? As well as things like looking for drift between a system as it's designed and built, and then as changes get made over its lifetime. An example of this might be that if I'm sitting in a SOC and I get an alert for CVE 2024 XYZ, maybe I can see from my network monitoring solution that it affects a certain PLC, and I can even maybe see that the PLC is connected to a certain type of equipment, like a pump here. But if I can see that I have two of these instances in my site, maybe one of these pumps is connected to the cooling process for my chemical process, and one of them is connected to like the plumbing in the break room. That's important information that I might want to know as I'm responding to it and might affect my prioritization. So that's kind of why we want to build the sort of graph model that we're going to talk about today. And the way that we're going to build it is through a combination of more traditional sort of IT tools like network monitoring tools, CMDBs, or configuration management databases, which will include things like software versions and other sorts of configurations, and the most interesting one for me today, at least, diagrams and documents. So we want to come up with a model that basically looks like this, where we can tie a CVE to a certain piece of software or firmware, see that that's running on maybe an engineering workstation or some other endpoint like that, and what networks it might be connected to, and then take all of that and put it in the context of our process, see what sort of physical equipment is that digital equipment controlling, and more broadly, what is the context of that equipment in our larger process? So as we mentioned a second ago, we can get the stuff in the blue box here from CyberTools, and that'll be our vulnerability reports and network monitors, things like that. But to get the larger context of how important is this thing that has the vulnerability really to our process, we need to go a bit beyond that. And for that, you would either need to go and interview the operators, or for our purposes today, look at diagrams. So the types of diagrams that we are looking at specifically are network diagrams, which cover both the sort of network and device level. Something called the loop drawing, which is basically taking the information of what digital devices are controlling specific pieces of hardware. And then P&IDs, or piping and instrumentation diagrams, are for the more sort of mapping functional assets to process level to see sort of if I have this valve that can be controlled, where is that in my factory or my ship? How important is it really? So these are just some quick examples of these. This one's from the SWAT project from the Singapore University of Technology and Design. We have a P&ID from the Open Industrial Data Project, and sort of the important thing here is just that these are all the little icons there are physical components, and they've got connections between them like pumps or pipes, things like that. And then this is what a loop drawing might look like, sort of taking the specific ports on a PLC to like a generator or a valve, something like that. So to make the graph, our basic plan is that we're going to identify and locate the very sort of concrete, low-level pieces of a diagram, things like text, icons, lines, and shapes. And then as a separate step, we're going to worry about the meaning of those and try to map them to a data model. Things like a line might mean a network connection, an icon and a label might be a network device with an IP, a dotted rectangle might be around a subnet, things like that. So we're going to do sort of a two-step process for this diagram parsing. Initially, what we were doing before all the AI stuff happened is traditional computer vision methods with human review. So in traditional computer vision, there's already a lot of algorithms that exist to do things like detect icons, lines, text, all that good stuff. So we would run those, annotate it, sort of draw a box around what we found with a little note, and present that to a human for verification or feedback, because obviously these systems aren't perfect, and we care about correctness here. Afterwards, we would do our sort of inference and mapping to the higher level data model and present the results to the humans again. When I first started looking at trying to take large multimodal models and put them into this, mostly out of curiosity, I tried seeing if I could do the whole thing with them, and that turned out to not work out so well for reasons that we'll get into in a second. But basically, the plan now, and what the rest of this talk is about, is using them to augment this approach. And so it's still going to be the same basic approach, where we are going to run traditional computer vision things, present it to a human for feedback, and then the rest. But instead, our goal with the large language models here is to run them sort of right before we give it to the human for feedback each time, ask them to, things like, does this text that we detected make sense? Are there any changes that you'd make? And with any luck, we can reduce the amount of changes that the human has to make so that in more cases, they can just look at it and say, yep, looks good, and don't have to spend time going in and moving boxes around, things like that. So what is a large multimodal model? I think a lot of people at this point have heard about large language models, or LLMs. They're basically these tools that you can put text into, and they'll do some sort of AI magic, and then they'll spit you out some text. Large multimodal models are basically the same, but they deal with more things than just text. So you don't necessarily have to just ask it a question and get an answer. You can give it an image and a question and have it answer a question about that image, things like that. They can do also, video, audio, all sorts of things. But for our purposes today, all we care about is that it's a tool that we can give in some instructions and an image and get an answer out in the form of text. But as we mentioned, they're not a panacea. They can't do everything. Some reasons that you might not want to just throw out your entire process and replace it with these guys is cost, somewhat. For the diagrams that we're looking at today with the corrections that we're making, it's still less than $1 per diagram. But if you have a really large bank of those, then this is definitely going to be a little bit more expensive than the traditional CV methods. Image size, a lot of these diagrams are actually pretty large, just in terms of resolution. And the large multimodal models have different ways of dealing with that. They might scale them down, or they might sort of run a sliding window across and look at different chunks one at a time. And of course, you can lose some information there. The really big one for us is going to be grounding, which is the idea of having the models tell us where they see the information that they're seeing and why they're replying the way they are. Because when they do make mistakes, and they do make mistakes, we want to see sort of what their process was there to try to fix it. And finally, they do still have trouble understanding certain concepts, mostly things like relative position. If you feed an image to one of these and you ask it, is a certain icon to the left or right of a different icon, they seem to have a lot of trouble with that. Initially, I thought maybe this was because I was dealing with graphs, which are like these technical diagrams, which are very sort of sparse, and that the tools were more trained on photographs and things like that. But it turns out that this is a problem even in the kinds of things they were trained on. If you give it a picture of a school bus and ask it which way the bus is facing, it still has a lot of trouble with that. So the current thinking, at least from what I've seen, is that the things that turn these images into the actual numbers that get crunched by the stuff inside, that they're losing some information as they're encoding that image, and people are working on new ways of doing this that'll hopefully fix that. But at least for the time being, we can't really trust them for certain sort of concrete details of what they see in the diagram and where that is in relation to other things. So we mentioned grounding. Just to go over sort of what that is in a little bit more detail now. This is the built-in grounding from GPT-4v. I gave it this image of a guitar, and I asked it to describe what it saw in as much detail as possible. And it was actually really, really good at this. It was able to give me the finish, the brand, the model, the number of strings, that it had some non-standard inlays, even the type of bridge and what that meant for what the guitar could do. And to get the grounding, it gave me two bounding boxes. One was in red, which is the guitar, which it's accurate. I don't know how helpful that is, really, but it's definitely correct. And blue, it gave me the headstock bears, which was a substring of the text that it had given me, and so this was related to that part. And it was talking about what it had seen there and what that meant, which it is, what it gave me the bounding box here for is relevant to what it was talking about there, but already we can see a slight mistake in that that's not actually the headstock of a guitar. So these things are not quite perfect. And ideally, I would actually like to get a lot more boxes than this. For example, if it's talking about the number of strings, I'd like to see where it actually saw that. But this is still better than what we get when we start giving these things diagrams. I gave it a similar sort of thing here. I gave it a subsection of a network diagram and asked it what it saw, and it was able to give me, there are these components with IP addresses. They're connected to each other like this. But it doesn't give any grounding. It doesn't give any bounding boxes. And so this is where we start getting into a problem where if it's making a mistake, we can't see where it saw the historian server. If it got an IP wrong or something like that, we can't really present that to a human. We can show them the diagram that it came from and say what it found, but we can't show where. We tried a few things to get around this, get the grounding other ways. One was asking for it in the response itself instead of as a separate piece of metadata that comes back. Tried asking it to give coordinates in various systems like this one here, where you'd mark up the image and ask, when you see this icon, is it in square A3 or not? Also asking it to give bounding boxes in terms of percentage height and width of the image, even with drawing lines, and asking it to use those as reference. And none of these really worked for the reasons that we discussed earlier with the relative position, I think. So that didn't really work. And so as we said, this is an example of some of their not being great for the concrete details. These are some bounding boxes that I was just trying to give it some really obviously bad ones and see if it could tell, that's a bad bounding box. And both of these said, that looks A-okay, even when I was specifically asking it, make sure it's not cutting part of the icon off, make sure there's not too much blank space, things like that. So basically, we can't trust these things, at least yet, for these really concrete details like that. And instead, what we're going to do is we're going to fall back to those more traditional computer vision approaches and then ask the LLMs more about the meaning and high-level stuff, just as a reviewer, like a human would. So now we're going to go through basically the way that the document parsing works and what we're currently doing. The first step is to extract text. There's a whole bunch of OCR tools that work pretty well for this, but still make a few mistakes. They might have some missing or wrong characters. They might have some false positives. And so as a model for what we're going to do with the rest of the process, we're going to go through the text extraction in a little bit more detail here and see how we use the large multimodal models to help with that. So basically, we're going to take any of the detected text that has a low confidence score that the algorithm wasn't super confident in, and we're going to give it to the large multimodal model and ask it for some feedback. I haven't put the whole prompt on screen because you wouldn't be able to read that, but basically what it contained was some context on what we're doing. We're trying to parse some diagrams into a machine-readable format. Some examples of the kind of mistakes that we're looking for, things like missing a character or the things that we just mentioned, a copy of the original image, as well as a copy of the image with a bounding box around the specific piece of text that we're looking for, because these OCR tools, unlike the LLMs, actually are good for giving you a bounding box around what specifically they've seen. And then finally, we gave it the detected text that the OCR tool spat out and the expected response format that we wanted it to return to us, which included some observations and reasoning about why it was making the corrections it was making, as well as the new text that it found, which might be nothing if it was a false positive, or might be the same as the original text if the original text was actually accurate, or might be something improved. So some examples of this. This was one that the OCR tool detected an extra 1 from this dotted line over at the left there. And when we gave it the prompt that we just saw on the last slide, the large language model came back and said, oh yeah, the detected text includes an extra 1 at the beginning that's not present in the image. and so it was able to fix that up for us. And that's one sort of fewer correction that a human's going to have to go in and do manually. So for that part, it starts to look pretty good. Here was another one where the tool detected this piece of an icon as a string of dots, and the LMM was again correctly able to say that, oh, this isn't actually a piece of text, this was a false positive, basically. The interesting thing here is that the text isn't, the reasoning that it gives isn't 100% accurate. You can see that it's saying that these dots are aligned between elements in a diagram, which is not what's going on. And this is something that I'm still trying to learn more about, where even if the reasoning isn't always accurate, it does still generally get better results at the end, one way or the other. But I think this also just sort of underscores that we can't, trust these things completely. We still want to have the human in the loop for this. One more was another one where it was another false positive, and the LMM was able to correctly say, yeah, this is not a piece of text. This is part of this sensor here. Once we found the text, we're going to block it off and just sort of erase it so that it doesn't interfere with the rest of the process. To get icons, we're going to fall back to some, again, traditional CV methods, things like shape detection, where you can find sort of circles and squares. Morphological transforms, which is what we're seeing on the pictures here. And that's basically a way of taking thin lines, and you can erase them and leave us with just these sort of big, thick icons, which we can then find and draw boxes around and present to the either like a neural net to classify them or the LLM itself. And finally, template matching. You can actually, on these, not so much on the network diagrams where people seem to just Google image search a computer and throw it in there. With the P&IDs and the loop drawings, these things actually tend to follow standards pretty well. And so once you find a specific sort of subset of pixels that represents a valve or a pump or something like that, you can put that in and just sort of match it almost verbatim, and you'll get some good results from that. Again, once we find these things, we're going to get the sort of bounding area and mask it out to run the final step of the concrete portion, which is getting the lines. Lines and shapes we get from something called the Hoff transform, or contour approximation for curved lines. And then we can start getting into the interpreting part. And so for things like that, you might look, if a line is going along and it ends, you could look for an icon that's intersecting the sort of projection of where it would be, and start using things like arrowheads to infer direction, things like that, and basically apply some of these heuristics and fall back to something like an LMM when those heuristics fail. And this is where the LMM is actually really good at these more sort of higher level conceptual things. So here's an example where if you're using a simple heuristic of looking for something that intersects the extension of the line here that's been highlighted in green, we don't find anything. But doing the same sort of thing that we did with the text, where we take sort of a small piece of the image and we give it some context on what we're looking for, the LMM was able to successfully say, oh, that should be related to this text here, and it's actually like a label for this line. In terms of building the actual graph, we need to associate the text with objects. Maybe that's with lines like we just saw. Maybe that's with icons, associating an IP address with the computer that is right above, things like that. And this follows, again, basically the same pattern. Apply some heuristics, and then see what the LLM thinks if we encounter a situation that we're not quite sure on. So for example, here on the right, we have this text wireless RIO, and it's pretty close to a few different icons, so just taking the nearest one is not necessarily going to give us the right answer. But in this case, giving it the LMM, this example with the different icons highlighted in different colors, it's able to say, oh, well, the pink one has a label already, and the text is using the word wireless, which we see this wireless icon in the green box, so it's probably related to the one in the green box. And that's the kind of sort of reasoning and logic that the LLMs are actually really good at. For new icons that we found with the morphology stuff, we can basically treat the LLM as a fancy classifier, where instead of just giving it sort of an icon and asking it, what is this icon, we can give it the icon in the context of of the broader graph in case that adds some extra information. Finally, we can take a bunch of these different diagrams and sort of connect them together. So when we were looking at the line here, when it says like solvent from unit 1, we're able to sort of connect that and find the solvent line in unit 1, take them all together, and then we can represent sort of the entire site from these separate graphs. This was an example of, again, this sort of using the LLM as a fancy classifier, where we, on the left here, highlighted an icon in red, and it's able to tell us, oh yeah, this is like an endpoint that a user's interacting with because it's got a screen and a keyboard, so we can map that into our data model that way. So in the end, what we get is a big fancy graph that might look something like this, or at least a small part of it might. And just to sort of tie back to why we were trying to do this in the first place, maybe we can do something like look at a CVE that we see that came in and say, oh, this is a 7.2 on the base score. But we can see from the P&ID that it's controlling this generator that's really critical to our process. And so maybe we want to increase the priority a bit. From the network diagram, maybe it's behind a firewall, so you can reduce it a bit, things like that. Or it's in a network with Purdue level 1, so that'll increase the risk. And you can start to use things like this to sort of prioritize your vulnerabilities with more granularity than just the CVSS score. So sort of just to summarize, large language models are good for the sort of holistic context part, but not yet for the sort of finer, concrete details like what is to the left or right of a certain thing. And the way to get around that, at least for now, is to detect objects first with other reasoning or other means, and then ask the LLM about the sort of the reasoning and meaning and what it thinks is going on at a more sort of abstract level. Some other just sort of quick tips that will affect your output if you're trying to do this yourself. Model size. I did find some other models than GPT and Gemini that were using different sort of image encoders to try to get around this positioning thing. And they, being open source models that were sort of designed to run on small hardware, they seemed to have a lot of issue just following the instructions at all. So I couldn't really tell if they were getting more information out of the images or not. But definitely, there seems to be a lower band on what model size is useful. As we mentioned back at the start, the image resolution, if you give these things an image that's too big, they're often likely to either compress it or run a sort of sliding window over it, which will affect your results. So if you don't know exactly how it's going to do that, it could be better to chop things up and give it the smaller sections yourself where you can control that. Examples in few shot prompts, basically giving it a few examples beforehand of these are some inputs and outputs that we would expect from this step and the kinds of information that we want you to take into account. It's able to learn pretty well from that. One versus several images, again, when we're giving it like the original image and then the marked up image with boxes drawn over it and things like that, presenting those as two separate ones instead of as one where they've been put side by side helps. And finally, asking for reasoning. The way that these things work is that it's all sort of probabilistic based on one word leading to the next. And so if you ask it for its reasoning specifically before it gives you any answers, that helps the quality a lot. If you ask it for the reasoning after it gives you the answer, then it'll just come up with a whole bunch of ways to try to justify whatever snap decision it made. So getting them to try to put off coming with a final answer for as long as possible and sort of think out through their process first is really helpful for that. The sort of takeaways of why I think you should care about this. One, for data quality, human review is still important. There's a lot of hype about AI stuff going on right now, but as we saw, these things aren't perfect yet. They still can make some pretty silly-looking mistakes, and so for critical infrastructure and things like that, where you actually want to be correct, I think you still really do need a human in the loop. But also, as we saw, they can be used to augment existing workflows. They don't have to replace them entirely, so we can keep the human in the loop and sort of gradually reduce the amount that the human has to do and increase the amount that the machine can do as we grow our confidence in the system. And finally, they're still evolving in a really big way. So things like that relative position issue might not be a problem in a month or a year, because the space moves just incredibly, incredibly fast, and people are publishing new findings on it all the time. So try to keep up with that. That's all I have. If you got questions, I'm happy to answer. And thanks for coming.